We'll move on now to our next speaker. So our next speaker is Dr. Martina Favero from Stockholm University. She's going to be talking about a stochastic epidemiological model to analyse the impact of non-pharmaceutical interventions on both the reproduction number and the generation time. So I'm going to hand straight over to Martina. Thanks very much for giving a talk.
Thank you for introducing me, and thank you for inviting me. So I'm going to talk about an ongoing work with my advisor, Tom Britton, and Gianpaolo Scagliatomba. And we are presenting a stochastic model that is based on infectivity process and is akin to Kermack-McKendrick theory. And we want to model different non-pharmaceutical interventions to see what is the effect of them on the generation time distribution. And this is important, as we have seen already in the previous talks, to estimate the basic reproduction number and effective reproduction numbers. The model is quite general, but we are going to tune it to COVID-19 to see some illustrations. Okay, so we assume that the population is homogeneously mixing, and that all individuals are at first susceptible, and that they might get infected at some point and later removed. And instead, infectious individuals are not infectious all in the same way, but they have infectivity profiles that are independent and identically distributed. I'm sorry, but I'm not seeing my slides on the screen, so maybe do you see them?
No, we can't see them either, I don't think. So hopefully someone
sorry.
will show some slides.
Let's see, I will try to share them again.
Ah, great. So it says you started screen sharing, but I think, yeah, there we go.
Okay,
yeah,
great.
Nice there, that's great. Thanks.
Okay, so likely there were no pictures in the slides so far. Okay, so as I was saying, that all infectious individuals have infectivity profiles that are independent and identically distributed, and they are the realization of a stochastic process lambda of t, which we call infectivity process, and that is the product of a contact process C and an infectiousness process X. And here we're measuring time since the infection of the infectious individual we are looking at. So a bit more about the processes that are involved in the model. So the contact process, we assume it to be piecewise constant. So each infectious individual starts with a base contact rate C1, and at some random point tau, this individual will reduce the contact rate to C2. And the random time tau, depending on the scenario we want to represent, can either be for example, symptoms onset or detection. And I will say a bit more about this later. But first, let's say something about the infectiousness process. So if we assume that each individual has contacts at a certain rate C of t, then at time t, a contact will result in infection with probability x of t. And the infectiousness process will measure the medical strength of infectiousness. To refer to something that all of you know, the SIR model, for example, in that case, the infectiousness process would simply be the indicator function over the infectious period 0i. But if we want to make things a bit more general, we could also choose a shape like this black line, so deterministic shape, and then use some random variables x1, x2 to move the peak of infectiousness up and down, or earlier or later, so that we can represent that different individuals have different infectiousness profiles. And then we multiply T and X, and we get this infectivity process, and each infectious individual will infect other individuals at the time points of a Poisson process with intensity lambda of t. Okay, so in this framework, we can write down the quantities we are interested in quite easily. So let's denote by g of t, 1 minus the cumulative distribution function of this random time tau. And that can also be written as an exponential, where alpha tau is the rate of tau. And then we have an infectivity function, which is simply the expectation of the infectivity process lambda. And in this setting, we can write down the basic reproduction number as the sum of R01 and R02. And you can see it from here that R01 is simply the average number of individuals that are infected by a typical infector before random time tau, so before showing symptoms or before detection, depending on the scenario we are looking at. And R02, that's the same, but after the random time tau. And it's quite easy then to derive the generation time probability density function, which is simply the ratio between the infectivity function and R0. Okay, so let's start by defining the random time tau when still no interventions are in place. So we could say that for COVID-19, a good choice would be to say that when people are showing symptoms, there is a reduction in the contact rate, a natural reduction, even without interventions. And so we could define tau as the time to symptoms onset, and we assume that the rate at which symptoms appear, this is proportional to the infectiousness profile. So at time t, it's going to be proportional to x of t. And this corresponds to saying that the higher the infectiousness at some time, and the higher the rate of showing symptoms, which is in line with what many studies have shown, that usually symptoms tend to appear around the peak of infectiousness. And we are also taking into account asymptomatic people in this model because this random time TS can also be equal to infinity, meaning that symptoms do not appear at any point. And that we can write down as this exponential here. Okay, but what is maybe more interesting is what happens when interventions are in place. And I'm going to simply focus on non-pharmaceutical interventions. And I'm going to start by talking about interventions that do not modify the time at which the contact rate is reduced. So when tau is equal to time of symptoms onset. So of course, one could consider when all contacts are uniformly reduced over the population. So for example, if some social distancing is in place or some lockdown, and that would correspond to saying that the whole contact process is reduced by a fraction rho between 0 and 1. But as you can imagine, this will not affect generation time distribution. Of course, this will affect the reproduction number, but not the generation time distribution. Otherwise, another measure which will instead affect the generation time distribution is isolating symptomatic individuals. So say that instead of, so when someone is symptomatic, instead of reducing the activity to C2, the contact activity is reduced to rho C2. And ideally, rho should be close to 0, so that symptomatic individuals are completely isolated. Of course, another measure that we often see is face masks, and that would correspond to reducing X, so the infectiousness process, by a fraction rho. But of course, this is interesting, but from a mathematical point of view, in this model, this is completely equivalent to measure number 1. So far, I've talked about measures that do not affect the time at which the reduction in the contact process happens. But instead, there are some definitely important measures that do affect the random time tau. So for example, instead of choosing tau to be the time of symptoms onset, we could choose it to be the time of detection. And detection could, of course, occur by different measures. And I'm going to focus on screening and contact tracing. So in that case, the time of detection would be the minimum between time of symptoms and time of screening, or symptoms and contact tracing, or the three of them together. And I'm going to focus now on this number 2 and number 4 and show you some illustrations about that. And contact tracing is something we are working on right now. So it's something we will maybe discuss in the future. Okay, so here, these are not supposed to be estimates of reproduction numbers or mean generation times, but rather an illustration of how things change because of interventions. So we have fit the model so that the numbers are in line with what people have been estimating. But you can see here, so I'm assuming that tau is the time of symptoms onset. So each individual will start with the contact rate, which is given by a random variable C1. And at symptoms onset, that rate is reduced by a fraction rho. And I'm using this infectiousness process that is the one I showed you earlier. And you can see here in the plot that the generation time distribution does change quite a lot if we vary the reduction rate rho. So let's start with this blue line. That would correspond to no reduction in the contact activity when symptoms appear, and that is very unrealistic. So you can imagine that these first couple of lines, these are not really realistic, because even if there are no interventions in place, it is quite natural to maybe have less contacts with other people when someone shows symptoms. Even like with a standard flu, people tend to just isolate a little bit when they show symptoms. Instead, when no interventions are in place, we could expect some reduction at time tau. So I would say that no intervention corresponds to some of the yellow lines in here. And of course, when we isolate completely symptomatic individuals, so rho is equal to 0 here, then that corresponds to this red line. So you can see that the mean generation time does change considerably, even though we can assume that without interventions we have something around 7. It can drop to around 5 if we can isolate completely all symptomatic individuals. And of course, you see also that the reproduction number is lower. And here maybe it's interesting to notice that R01, which is the average number of individuals infected before symptoms, that doesn't change. This measure doesn't change R01. So even in the best case, we can never go below 1.64. And as a consequence, even the reproduction number cannot go below that threshold. Okay, and I forgot to say that in this scenario, we are considering that about 1/3 of our cases are asymptomatic. And so you can imagine that in that case, well, this type of interventions does not affect 1/3 of cases. Okay, but what happens when we introduce some screening rates? So let's say that each individual has a constant rate of being screened, and that the random time tau, that is the minimum between the time of symptoms and the time of screening. And so the rate of tau is going to be of this form. And you see here in this table what happens to the mean generation time. So we are starting from this line, which corresponds to the last line of the previous table. So we are isolating from completely all symptomatic individuals. And on top of that, in the second line, so in the rest of the table, we are increasing the screening rate. And you see that that, of course, changes the mean generation time and also a little bit the shape of the generation time distribution. And unfortunately, I would say that a big effort in the screening, in hiring the screening rate does not give huge results on R0. For example, here the second line and the third line, for example, would correspond to quite a big effort in screening. Imagining that we could reach higher screening rates up to this last line would be unrealistic. But if we imagine that in the screening rate, perhaps we are including some contact tracing, then we could say that maybe these last lines could be reached in practice. But so what we are doing right now is to model contact tracing in a proper way. There is not so much time left, so I'm just being very quick about this. If we want to model contact tracing, we should define some rates at which an individual is contact traced through either people they have infected or through the person who infected them. And we do have some heuristic formula for those rates, but they contain quite implicit expressions. And they also imply an integral differential equation for the rate of tau. So we're trying to make this a bit more usable in practice. But already without including screening, it's quite clear that non-pharmaceutical interventions can indeed shorten generation times. And so if we use estimates of generation time distribution from the early phases of the pandemic, we will see biased estimates of reproduction numbers, for example. And so there is a great need to either collect data for up-to-date estimates of the generation time distribution, or otherwise, at least we should account for biases through a model like this one that includes interventions. So here is some references, and thank you for your attention.
Thanks very much, Martina. That was great. Thanks for your talk. There was one question about the reduction in contacts in your isolation strategy. And it seemed like you assumed that the reduction in contacts applied exactly at the time of symptom onset. And the question is, what happens if that reduction in contacts appears slightly later? So for example, maybe initially symptoms are non-specific, and so it's only slightly later that the person chooses to isolate. What effect does that have on the generation time and the reproduction number?
Yeah, so this model so far is quite basic. It could be, well, I mean, at least the examples I've shown you are quite basic, but it has the capacity of including something like you described. So, and that would be easy by simply assuming that tau is not the time of symptom onset, but just, you know, plus some epsilon or some other time, which you can model in any way you prefer.
Cool, sounds good. Thanks very much. And there's one other question, which is to do with the impact of asymptomatic infections. So basically, is it possible to account for asymptomatic individuals in this framework? And this person says that it would affect the performance of the first approach, perhaps, so the reduction of the time from the time to detection from symptom onset. So yeah, is that something you've considered, the potential for asymptomatic transmission?
Yes, I did have some plots on asymptomatic generation times, but there was no time for that. Yes, of course, asymptomatic do have a huge impact on this particular measure, this isolating symptomatic individual. So if you have a lower fraction of asymptomatic cases, then you would see bigger changes in the generation time distribution, and if the fraction is higher, the other way around. Yeah.
Okay, sounds great. Thanks very much. So I think there aren't any further questions. So thanks again for your talk. That was excellent. And